All right, so I think we should pick it up where we left off last time. We were still talking about VBA, which we'll wrap this discussion today, and then get back to the new material, which is section 4, the forward and futures contracts. Okay, so um, today we'll wrap up our detour into the world of VBA. I want to show you some more of the key features of the language because we'll definitely need these as we go along. And then I'll show you a couple of examples of how this works. And then, like I said, as soon as we're finished with this, we can start talking about forwards and futures, which are the two most basic types of derivative securities. They're the least mathematical, but they're very interesting. And we'll see that they're very heavily used in the markets for hedging purposes and sometimes for speculation too. And then after that, we'll dive into options where we'll spend pretty much the rest of the course talking about options and how to price them, as well as how to develop trading strategies with them. So here's an example from our very extensive list of VBA examples, which I've opened up for you. And so we'll go back to our VBA code examples, and we'll open up the developer tab. And under Visual Basic, you'll see that we want to now examine VBA example number 12. And let's see, where are we? There we go. Now, it doesn't look like much. It's a fairly short program, but it's an awfully important one because we're going to, for the first time, actually use matrices. All right. So and as we get later into the course, we'll be using matrices more often to implement the pricing models that we'll be interested in. So first of all, let's remind ourselves of the key details here. We have, well, for each procedure, as we call them, it can either be a subroutine, which is also known as a macro, or else it can be a function. This one happens to be a subroutine. Now, usually we pick subroutines if we're pretty confident that we'll need to produce more than one output. Functions are very important, but they're restricted to a single value coming out of the function. Here, we can have as many as we want. So we start with the name fill. What we're basically going to do here is fill in a matrix. Okay, now, of course, VBA doesn't actually use the word matrix. As far as it's concerned, a matrix is a two-dimensional array, which means it has both rows and columns. So we start out dim. Remember, that tells us that we are defining variables of a specific type. Here, I and j are the indexes we'll be using. I will represent the rows, j will represent the columns, and we want to make sure that they're integers, all right? It doesn't make any sense, for example, to have an index of 3.7. So just to be on the safe side, to make sure there's no mistakes, we'll define this as an integer, although this part is optional. It's a good way to help yourself avoid issues. Okay, so now my array is the array that we're going to fill in, and if you notice, it has been indexed with rows 1 through 5 and columns 1 through 5. Okay, so we'll use the traditional notation. We'll have rows from 1 to 5 and columns from 1 to 5. So in VBA, when we define an array like this refers to the rows and this refers to the columns. And once again, we want our matrix to only contain integers, so we put in the keywords as integer. Now, how do we fill it in, though? Okay, here we just defined the matrix that we want to create. My array will be a 5 by 5 matrix. How do we fill in numbers? Well, there's a lot of ways we can do this, but here for the first time, we're seeing something very interesting. We have two for next loops. One within the other, and these are said to be nested because one is contained within the other. Now, by the way, if you notice, they each need a next statement. So the outer one, this outer loop, is where we'll increment the rows. We'll go through the rows one at a time, and then within each row, we will do this, which means we'll fill in all 5 columns. Okay, now, what will we fill it with? All right, well, for example, actually, let me draw a quick sketch here. So what it's saying is that we start out with when I is equal to 1, meaning row 1, we go to the first column, J is the columns, and we'll put in that cell I times J. Now, the way this works is that it sees the next J, and that means it jumps up to J equals 2, which means we're going to cell 1, comma 2, right? So up here, we're still in row 1, and then we're going to go through all 5 columns. So the next cell that we'll consider is 1, comma 2, and we'll multiply I times J, which is 1 times 2. Then we go on to J equals 3. Okay, so here I is still equal to 1. Now J is equal to 3. So we go to that cell and we multiply 1 by 3. Then this goes to 4. We multiply 1 by 4, and then 5. Fill in the 5. Now this loop is completed. So we move on to I equals 2. And we start all over again with the J's. Okay, so we have to go back to 1. So, and here we have cell 2, comma 1. The product of those two is 2. Then we go on to the next J or column. Here at 2, 2, we multiply 2 times 2, which is 4. Then we go on to the next column, which is 3. And then when the product here is 6, we go on to the next row, column rather, which is 4. And then we go to the last column, which is 5. And we put in there 10. Okay, now this loop is done. We go back to the top. This now becomes 3, and we start the J's all over again. Okay, so we start, J will now be 1 through 5. So here we're looking at cell 3, comma 1. We go on to the next column, 3, comma 2, 3, comma 3. Oops, no, we don't scratch that one out. 9, 3, comma 4 is 12. And then finally 3, comma 5 is 15. Great. Now it's time to go back to the top. For row 4, we start the columns all over again. All right, let's do it. So here we have 4, comma 1, 4, comma 2, 4, comma 3, 4, comma 4, and then finally 4, comma 5. Great. And finally, we're ready for the last row, which is 5. We start the columns all over again. And I think you can see now where this is going. So here we have 5, 10, 15, 20, and 25. And that's our matrix. And then we're done. Now, then we get down here to when the next I, when we're done with all 5 of them, both loops are completely finished and we end the subroutine. So there's our matrix. So now, if we want to, we can print this out. But the bottom line is that's what it looks like. So the code here doesn't. Oh, yes, it does. Here, I'll tell you what we were missing here. I just realized. I kind of was overlooking it. Every time we did this, I just realized I was paying so much attention to filling in the matrix. We also have this command cells I dot j or I comma j dot value. And what that's saying is put those out on the spreadsheet. Okay, now if you notice the notation is I comma j, this is the row, this is the column. So what was happening was that every time we filled in a new cell in the matrix, we were also simultaneously printing it on the spreadsheet. Okay, now Excel understands how matrices work. So when I tell it cells I comma j, for example, 2 comma 3, it knows that I mean this one. Okay, so yes, sorry, I completely overlooked the printing right here. We were not within each loop, we were not just putting values into the matrix, we were printing them out and with this command cells, just to make sure that it worked correctly. So if we execute it right now, you'll see what happens. We go to the macros and we find the one we were just working with, array fill, and there you go. And it works beautifully and quickly. Now, of course, I can fool around with this. I can make changes. I can change what I want here. For example, instead of I times j, I can have something like, oh, I don't know, the square root of I times the cube root of j. I can have anything I want. But the important thing is that the cells are being filled in. Row, we go through within each row, we fill in each column first, and then we go through all the rows, and then when we're done. So now, what if for some strange reason, it needed to be the other way around? Okay, in other words, if you notice how you did the first row, then the second, then the third, the fourth, the fifth, within each row, I did all the columns. I could easily reverse that. I could go column by column, and within each column, do all the rows. All I would have to do is reverse the roles of the I and the J. Okay, it would not be difficult to do that at all. Okay, J would run from 1 to 5. In fact, I'll tell you what. Now, actually, the only problem is you wouldn't be able to see the difference. What you'd end up doing, I'll just move it down here. All I have to do is reverse these two letters. The only problem is, like I said, you would never notice it when you're looking at the printout because it happens so fast. And so that way it would go through the columns first. Within each column, it would fill in all the rows. For a case like this, it makes no real difference. But there could be other cases where it does matter a great deal what order you do this in. Okay, so the bottom line here is that we now understand how a nested loop works. And we know that this is telling it what values to assign to the elements of the matrix. And this one is telling it where to print them. Okay. Now, here's something we can experiment with. What if this is not a great place to put my results? What if I'd rather have them in a slightly different location? What I could do, something like this. Let's see, one of these buttons will execute it directly. Yeah, so you see what I did? I just told it to shift over 2 columns and shift down 2 rows. It was a very straightforward thing to do. So let me take these out of here. We don't want these to be permanent. Or if you wanted something else in your cells, like for example, what if I want 5 times I times 4 times J or something like that? No problem. Actually, you might want to clean this out before. There's a command you can use to do that for you, where it just erases everything and then before you start all over again. But let's just see what happens here. Yeah, see, it just it just scaled the numbers up. All right, let's get these out of here. Other things we could do, for example, instead of 1 to 5, we could have had 0 to 4. But then if you're going to do that, you have to make sure that these formulas line up with that. But you can have, like we were seeing the other day, you can have indices that have any values we want, as long as they're integers. I don't think it'll allow for fractional indices, but it certainly will allow negatives, which is very unusual for most programming languages. All right, well, anyway. So these are, yeah, we've pretty much already gone through all this. Now, do until. Now, this is a little different. What's you see here, we know in advance we want a 5 by 5 matrix. So we use a for next loop because we have to specify how many elements are in each loop. But what if that's not true? What if we do not know what the size of this matrix will be until we have further results? Well, then you can use something like this, do until, which means keep going until a certain condition has been met. And we don't necessarily know when that will be. Let's say, for example, it's possible that we end up with 10 loops. It's possible we only need two. So this structure is better when we don't know in advance how many rows and or columns we'll need. Like with this one, now this one is a function and it says do until loop and is integer, meaning I'm going to give it an integer. And I'm going to create some intermediate variables. These variables only exist within the body of this program, by the way. These are not being read to me from the outside. These are being used for internal calculations. So we need something called my result, which is an integer, and then x is an integer. Now, also, here's a good programming practice. When you have variables like this that are defined inside your program, you may want to tell VBA what value they should start with, and that value is often 0. Because if not, well, let's just say that you don't want to make too many assumptions. It's easy to say, well, it'll assume I mean 0, right? Not a good assumption. You don't know what might happen. So in other words, this is the only way I can guarantee that my result will start at 0 and that x will start out as 1. Now here's the do until loop. Do until x equals n. N is the number that I passed to this function. Until that happens, every time I go through this loop, I'm going to take my result, whatever it is, and add 2 times x to it. And notice here, I'm going to then increment x by 1. Okay, so then, now, by the way, if you notice, the do until requires this loop to tell it that that's the end of the loop. Now, because it's a function, I have to somewhere assign a number to this do until loop, which I do here, and then we're done. So the tricky part is often trying to figure out what's happening in each loop. So here, for example, what I did was I said, well, let's try this with x equals 4 and see what happens. All right. So let us run this function, which is do until loop with a value of 4. It doesn't matter where I put it. Here's the do until loop. And it comes back with 12. Now, here's the thing. How do we know that it's 12? Okay, well, here's what's happening. First of all, it's going to run until x equals n. So initially, x equals 1. So we have x is 1. And at that point, my result is 0. Oops, sorry, my result is 0. So those are the initial values. Oops. Now, once we get into this loop, the result will be incremented by 2x. Let's call this new my result. And that means we take this number and add 2 times x. Now here, we have to make sure it knows that x, every time we go through the loop, goes up by 1. So this my result equals previous my result. So in other words, what happened here was that we added, and by the way, let me add this so we can remind ourselves what's actually happening. Okay, so in other words, my the new result, as I'm calling it here, is equal to what it was plus 2 times x. Okay, now x goes up by 1. This result is what I had in the previous loop, and now I'm adding to it 2 times 2, which means I've added 4 to it. Okay, so now I should be able to drag this down. Now what number did it gave us 12, so we won't reach this point. Um, because it says do until x equals n. When n is 4, it stops. End of story. Okay, so in other words, when x is 3, my result was moved up to 6. Then we add 2 times x, which is 6 to that, which is 12. And then in the next loop, when the program sees that x equals 4, it stops. End of story. So the result that you're seeing here is the 12, not whatever would have come next. Okay, if it had carried on one more, it would have been 20, but instead it stopped at 12. So see this one, there's a lot going on here. But the bottom line is it knows to stop. So we end up with 12. Now do while is the same thing, except that it stops um, one step sooner than do until. Okay, so if I run this one as do while, oh, this time it ran to 12. What do you know? That's interesting. So it stopped after 3. Just check some. Hmm. Okay, so let's look at the code then. So this is 13. Oh, this isn't the do while. What happened to do while? This is do while. The do until doesn't seem to be. That's strange. I thought I had both of these here, but I don't know what happened. No, oh, this says four. Oh, it's 14. Oh, oh, I see what happened. The code here is written as strictly less than n. Okay, I'll tell you what, let's run it like this. See, I think I must have done it on purpose to make sure that they turned out the same. If we run this one now, do while, this is do until, do while with 4. Oh, no, that's interesting. It turned out, oh boy, this is what you get for messing around with it. Oh, yeah, yeah, yeah. No, you see, I know, okay, because it's wild, it stopped after one loop. Okay, let's try that again. Wait a minute, what happened? There it is. Okay. Mystery resolved. All right. So in other words, by having this less than or equal to and having this one equal to the do all right, actually, you know what? Just let me just label this. Let's do just to make sure we know which is which. Do until loop gave us a result of or do while written like this, in other words, with less than or equal to, means do while loop for will give us the 20, which this is what you would have gotten here if you're going on one more step. Okay, so the until stops. When it sees the for, it stops. With the while, when it sees the for, it carries on for one more loop. That's the main difference. Okay, so that's what this is meant to illustrate. Do while or do until loop stops when x equals 4. Do while loop stops after x equals 4, meaning that it continues for that one more loop. So you would use the one that reflects what you actually want it to do, but you can see you could use either one of these. All you'd have to do is adjust this number, this right here. Now, based on what we'll be doing in this class, the chances are pretty good. You'll most likely be using the for loops. This will be the one you're most likely to use because we should know in the beginning how many times we have to loop through the function. There's no real great mystery about it. But for other applications, then these can become very, very helpful. These do while and do untils. Okay, but most likely this is the one you'll need. Okay, now what about some of these other more advanced ones? So like case, I mentioned this earlier. This is a good one. It takes the place of very complicated if then else statements. If then else is great if you have only one or two, maybe three conditions to juggle. But once you get past that point, it gets very, very awkward to write code for if then else, then else, then this, then that. So case is meant for cases when many different events can take place based on the value of a single variable. For example, what if we had there's a city where this the fine that you pay for speeding depends on how far over the speed limit you are. Let's just keep it simple and have three of them. Now, again, we could have easily done this with if then else, but let's just say we'd rather do it a little differently. So 1 through 5 is $25, 6 through 10 is 50, and 11 plus will be 100. So rather than using a potentially complicated if then else statement, look how easy this is. We say function fine, speed is integer, as an integer, meaning that an integer goes into the program, an integer comes out of the program over here. And then here's the keywords, select case. If you see in the program, those will be in blue. There we go. And so we give it, and see, here's the genius of this. We can have as many of these as we want. I could have 20 different speeding fines, and it doesn't care. It's just as efficient. And so you can see all I have to do is say, well, if it's 1 through 5, the fine is 25. 6 through 10, it's 50. And then you notice here I can use a statement like this. Anything from 11 up is 100. And then now I need this end select statement. You can see how easy this is to set up. So when we did that grading example a while back with the if then else statements, this might have been a better way to go. Okay, it's just that at the time we were learning if then else statements, but probably if you were writing this program now, you would want to use the select case because there's at least 5 different grades you might have to deal with. So you can see it's a very helpful function. Or actually, it's not a function, it's a control structure. Sorry, these are all known as control structures. Okay, what else do we have? Go to. Now, This is a blast from the past, let me tell you. This is going back to the ancient days in computer science, like the 60s even, where the whole point of it is that if you run into trouble, you have like a line of code that says, here's a case that we're not so sure what to do with. Then just go to this line and do this. It's basically a way of, it's sort of like a way of getting out of a trap. So you can see here we have function odd even number as integer as string. So in other words, we're going to read in a number, and what we're going to do is print out letters that spell out either odd or even. But we know that somebody may make a mistake and they accidentally give us a number that is potentially non-positive. In other words, negative or zero, which we odds and even only applies to positive integers. So if that happens, we could right then and there produce an error message. The thing is, we don't want the program to continue if this kind of mistake is reached. So by saying go to error, which is, by the way, down here, this stops execution of the program. It says, whoop, oh, something's wrong here. Let's just knock it off and produce an error message. And that way it doesn't go through all these other steps. So that was one of the advantages of it. But it does make the code a little bit more difficult, let's say, to follow the logic. But here we're seeing that if that's not the case, then, by the way, num mod 2 equals 0. This is kind of an interesting thing. Mod is short for modulus. What this is saying is that if you take your number and divide it by 2 and you get no remainder, then that is defined as an even number. Mod 2 means you divide by 2, and we see what we're looking for is just the remainder. If the remainder is 0, it must be an even number. If not, if it's anything else, then it must be an odd number. So this is kind of a tricky program. And also, because of the presence of this error message, which is known as a label, by the way, we need this extra step in here, exit function, which means if we did not have this error message, we can stop right now. Okay, so it's easy to forget that you need this part. So let's go get the code. And you can see now the exit and function are all in blue. So let's run this even odd, or odd even rather. Oops, not that. I tell you, what I'm going to do is put some numbers here and see how it reacts. Those we can do it more than once, very quickly and easily. Because it's a function, I can copy it and paste it to the other cells without having to retype anything. Oh, you know what I forgot to do? I want to check something like this. Yeah, see, now that means we didn't plan this program as well as we might have. You see what's happened here is we've allowed for the possibility that somebody puts in a negative. Now see here it says num is integer. That's very strange. It was supposed to. You know what I think must have happened when it says as integer, it may have converted it to the next closest integer, which is 2. Let me just try something here. That's okay. That's what I was afraid of. Yeah. So in other words, what it did was it said, well, you wanted this to be an even. So what I'm going to do is round it to the next even, next integer. So Uh-huh. So that means if we really and truly want to prevent anything but an integer, we do have to have some kind of error trapping in there that basically stops the function if you don't give it um, an integer. Wow. Okay. Now, scope of variables tells us where do they apply. There's three levels. Procedure level, which means only within that function or subroutine. The module level, which means everywhere within the same spreadsheet. And the public level means everywhere within that workbook. So in other words, this workbook, a workbook is the entire spreadsheet. Okay. This VBA code is a workbook. It has a lot of code built into it. It has a lot of functions that have been defined. And so if we want to make sure that a particular variable is only valid within, let's say, oh, I don't know, let's say we only want something to work within VBA example 16, we have the ability to make sure that the variable that we define only works within this module right here. So that way we can avoid naming conflicts with the other modules. All right, so now right now it's assuming that all these variables should always work, but we can override that by saying, listen, I'm going to define a variable new, let's say, and I only want it to work within VBA example 16. If that's the case, then it is going to be defined at the module level. Sorry, no, procedure level, my mistake, procedure level. If I only want it to work on a particular sheet, then it becomes a module level. And if I want it to be available to everything in that spreadsheet, then it becomes public. And that is the default, by the way. Okay. So here's how you take care of this. Dim or static defines it at the procedure level. Module means we can use private. Static. Dim, dim can mean something else. So I think we're probably better off using static for procedure level only, private for module level only, and public guarantees that it will be available everywhere. So let me show you some examples. So static is the same as dim, except that the variable is stored and is available the next time we run that program. So it never forgets. It knows only to use it within that module, but it also remembers it every time we open Excel. Private means all the procedures within a module, but not the others. And it sits on the top. It doesn't get embedded in the program. So in other words, here's one where we want to make sure that we don't end up using tax rate for other programs. Okay, here, this guarantees that it only works here. And then public just means everybody can use this function. The functions themselves too can be made public or private. Let's say there are certain functions you only want to use within a particular module. It can be done with the words public and private. Now, usually we just end up, I mean, for our purposes, everything can just be public unless there's a very good reason why we want to keep the functions separate from each other. All right, so that's our overview of VBA. Now, here's what we're going to do. We're going to go back to one of our earlier sections that I skipped over because I wanted to wait until we were done with our VBA discussion. And that would be the end of section 1, where we talked about yield to maturity. And I did mention that when you have a price yield curve, if you recall, what we're seeing here is the unique relationship between a bond's price and its yield to maturity. So you notice it's an inverse relationship, but it's also one to one. Okay. And that simply means that for each X, there is a unique Y, but for each Y, there's also a unique X. So that means I can invert this if I need to. But in the case of the yield to maturity, the pricing function is so complicated that it's usually not practical to find the inverse of this price yield function. So instead, what we have to do is something like this. Let's say that you know the yield of a bond is 6% and its price is 1,000. There's another bond with a 7% yield and a price of 950. What if you looked in the Wall Street Journal and found another bond whose price is 975? What you'd like to be able to do is calculate the yield yourself. Okay, so how do we do that? Well, basically, what you're going to do here is you know that 6% is too low, 7% is too high. So you're basically going to try other values in between. Let's say you try 6.5%, and that's a little too low. Then you raise it and see what happens. So in other words, you have to have a method that lets you search for the correct solution when you can't invert it like this. So there's a few different ways we can do this with the yield to maturity. And so one of those is called the method of bisection. The second is the Newton-Raphson method, and the third is the secant method. Now, they all have their advantages and disadvantages. And what we're going to do is see the code you would use to calculate the yield from the method of bisection. What's good about the method of bisection is that it's guaranteed to converge to the solution, but it might take longer than these other two. These second and third ones can be faster, but they also are not guaranteed to converge. So the method of bisection works as follows. So the first thing we have to do in order to make this thing work is, if you notice, you've got the price yield curve. The price yield curve is always positive. Notice, you can imagine it's in the first quadrant of the XY coordinate system. Okay, in other words, the horizontal and vertical axes are always positive. This method won't work if that's the case. So what we do, our clever strategy, is to take the price yield curve and subtract the whole thing from the whole thing, the price of the bond. Okay, so in other words, this 950 becomes negative 50 down here. So we shift the price yield curve. Is shifted down by the price of the bond, in other words, P dollars. And that means that this is what we're looking for right here. This is the yield to maturity of the bond. Right? Because what's happening at zero, zero means the price that we obtained using the yield to maturity is equal to the observed market price. So this is what we're aiming for. So here's what we're going to do. Let's see. Let's say we've done this. We've shifted it down. Here, let's say here's A and here's B. We're going to call this F of A, which is the price of the bond at yield A. And we're going to call this F of B, which is the price of the bond at yield B. What we're trying, and this will be C. Actually, no, not yet. We're looking for this point where they cross, but oh, all right, I'll just leave that there. What we do is we start by cutting the distance in half. Let's say that would be here. This is C, sorry. Now we have to solve for F of C. Now, here's the thing. This is the actual solution that we're looking for. The way I've drawn this, it's pretty clear that F of A is higher than the actual bond price. Which is right here. F of B is lower. Actually, I'm sorry, F of C is lower. Do we say then that A and C bracket the root? And that means that what I can do now is redefine this as B, the right side of my interval, and then I can find another C halfway in between. Let's just say that turns out to be here. Let me draw that a little straighter. Okay, that is the new C. This is the new B. Okay, so there's my C. Now, this time F of C is up here somewhere. That means that this can now become the new A. And then I define a new C somewhere in the middle here. Somewhere in between A and the new B. Okay, I'm having trouble drawing straight lines today. And voila, that's the correct value. How do I know that? Because F of C equals 0, which implies that whatever this is the market price. Okay, so in other words, what you're basically doing is you're taking an interval and let's say C is here somewhere. What you're, oh, actually, we'll call this P star for the correct solution. You're changing the interval until you get as arbitrarily close to the correct price. And each time you do it, you're cutting the interval in half. And so therefore we call it the method of bisection. So let's go through the slides for a second and see how that works here. You've got your price yield function after subtracting the price. So that means this is what we're looking for right here. At the moment, A and B bracket the root because F of A is above the price, F of B is below the price. Another way to think about this is that F of A, F of B is negative because F of A is positive and F of B is negative. And that implies that that product is negative. So C is going to be halfway between A and B, wherever that happens to be. Let's say it's here. And what matters now is right here, the sign of F of C. F of C is negative. So that means that our new interval is going to be because now we can see at this point, f of A and f of C, the product is negative, which means A and C must be on either side of the root. Now what do we do? Well, this C is now the new B, and we do cut A and B in half. And let's say we end up here, right here. That's the new C. Oh, look what happens here. F of C is positive. F of the new of this one is negative. So this is now our new interval here. So we're going to just keep cutting the interval in half and either redefining A is the new C, or sorry, C is the new A, or C is the new B, and we get closer and closer, and we end up eventually with the right solution. So C is always halfway between A and B. And when we solve for this, if f of c equals 0, that means we're done. If f of a, f of c is negative, that means a and c, bracket the root, if positive, they do not bracket the root. That means that will influence what we pick for a new interval. So in the second case, this is A, this is C. That means that this becomes B. And we'd find our new C in here somewhere. But in a case like this, C is way out here somewhere, so that can't be right. Okay, so our new C will be right here in the middle somewhere. And then as long as we're outside of a certain range, we're looking for the absolute difference between B and A when it gets within a certain amount. Now, we're never going to find the exact amount. We're never going to get it precisely correct. There's always going to be some error there. So we specify what the tolerance is. All right, so these two are a little bit more involved because they involve derivatives, but what I wanted you to see is this spreadsheet that has the code for method of bisection. So let's take a look at it. So we've got A and B. Here's A, here's B, and this is the bond. It's a $1,000 face value bond with a $70 coupon and a 4-year maturity. So the price is currently at $960. We want to know what its yield is. So we start out with A at 0.0001, and then we'll put B over here somewhere. We do this to make sure that C is in the middle somewhere. Okay, now you can see that it's already been run. The answer turned out to be 8.213%. But how did we get to that point? Let's go to the developer tab. By the way, here's one of the awkward things about this. When you have multiple spreadsheets open, it's going to be trickier to find what you're looking for. So I'm going to close the old spreadsheet. I'm going to put a new label on it. Okay, so then notice I'm going to leave this stuff here. Now I'm going to close it. And then now when I go to the developer tab, there should be only be one program listed there. There it is. All right. So let's see what it's doing. So it's a subroutine or macro. It's got variables A, B, and C, and F of A, F of B, F of C. We also have epsilon, coupon, face, and maturity. So this tells me where to read the information out of the spreadsheet. You notice how they're already here in cells B3 through 9. These are the inputs into the problem. So you see how I'm reading them in. A, for example, is cells 3, comma 2. In Excel, that would be read as the third row and second column, which in Excel is referred to as cell B3. So this is one of the strange things about Excel. Even though it understands matrix notation, the cells themselves are not labeled correctly in the sense that row 3, column 2, you'd think it would be cell 3B, but they call it B3. So you can try to use proper matrix notation, but you could also use, if you want letters, you could instead put, for example, and that is what you would have to do. Range B2 means cell B2 as opposed to the third row and second column. And then the others are all the same. Epsilon is the tolerance that we're going to have. In others, when we will stop this program when the actual price is within this much of the market price. I mean, or our model price, program price, I guess we'll call it, is this close to the actual market price. So while the absolute value of B minus A is greater than epsilon, meaning we're outside of the tolerance range, our C will be the halfway point between A and B. Now, here's an interesting twist. This program, the subroutine, I should say, has its own function down in the bottom. I did mention this once before, that a subroutine or macro can contain other subroutines and other functions. And here's one right here. What this is doing is it's evaluating the price of the bond. Okay, that's all it's doing. It says f of x, but that's because that's what we're calling this on our graph. Yeah, f of x is the price yield curve shifted down, but what we're doing in this function is calculating the price of the bond given the coupon rate, the yield, the coupon, the face value, the maturity, and the price. So that way, no matter what values we pick for A, B, or C, we can evaluate the price of the bond quickly and easily using this separate function. Okay, you can see why this helps because that way I can do that separately. I can price the bond with a separate function so the details don't mess up this logic. It's like I'm delegating this task to somebody else. I don't want to know the details. I just want it done. So that's why that function is down there. And so here we go. If FC is negative, that means the left side, the A becomes B. And then we look for our interval between B and C. Otherwise, we do it with A and C. And we stop when the epsilon is smaller than our tolerance. By the way, this is one control structure I just realized that never made it into the notes. It's called while. And basically, it's very similar to the other ones in the sense that what it's saying is that as long as this absolute value is greater than epsilon, carry on until it's not true anymore. And the keyword that matches this is called when. And that means stop when this condition is no longer false. When that happens, C is what you're actually looking for. Read that back to the program and you're done. Okay. So this is a fairly complicated piece of code, and the whole point of it is to implement the method of bisection. Okay. So that is a somewhat more sophisticated program than the ones we've been looking at. So this way you have a sense of what a VBA program might look like. And in this case, we just happen to be looking for the yield to maturity of a bond using the method of bisection. Okay. So now close this out. And this, I guess we don't need this anymore. So what remains to be done now is I think we're kind of done with our discussion of VBA for the time being. So I'm kind of looking forward to getting back into our discussion about derivatives again. And that would be section 4, where we're going to look at forward contracts and futures contracts. So this one, these are really the most straightforward of all the derivative securities that trade in the marketplace. A lot of this is just terminology, but there is some discussion about pricing issues. So we're going to talk about how to hedge, which means reducing risk. We'll see the differences between futures and forwards. And it'll be very interesting, but not terribly mathematical. But it gives us some insights into what derivatives are all about and why they're used. These are very popular products, by the way, forwards and futures. The volume of trading in these is just beyond belief. There's something like $2 trillion worth of foreign exchange forward contracts being executed every single day, which gives you some sense of how important this is. So we're going to do this chapter, and then when we're done with it, we can start talking about options, which are by far the most complicated of all the derivatives. And then we'll see how they're priced, how they're kind of strategies we can use in them. And it's the pricing that will really occupy a lot of our time, because options are very complicated to price. So we'll start out with a simple model, the Black-Scholes model, and we'll work our way up to the more complicated ones as we go along. All right. So anyway, I guess we'll save this one for next time. We'll be exploring derivative securities, namely forwards and futures, and then we'll carry on from there. Okay. So I'll see you all next time.